Hello everybody and welcome to the fourth episode of our tutorial Bayesian Inference, and in today's video I will talk about Bayesian linear regression, and I will start this video by discussing the reason behind employing the Bayesian approach in the problem of linear regression, and why do we need a new approach to handle the problem of linear regression. Up to now we have learned in this channel about two techniques to solve the problem of linear regression. The first one was the ordinary least squares technique, where we minimize the error function of our regression model. The second technique, which was the topic of the previous video, was about employing the maximum likelihood approach to fit the regression line. And in today's video we want to employ the prior and the likelihood in the Bayesian complete form to handle the regression problem. So usually when we adopt new technique or new approach to solve the same problem, we expect that we have some advantage behind this new technique. So let's have a quick comparison between these three techniques. As we have learned that the basic technique, the ordinary least squares approach, is mainly used to fit the regression line, and it works on batch mode, which means that each time we receive new data, we have to adapt or run our algorithm over all data set we have. On the second approach, the maximum likelihood approach, we have learned that we obtain a fitted regression line plus an estimated level of data noise or data uncertainty. This level expresses how we are confident about our prediction and what is the error ratio that can come with the predicted value using the maximum likelihood approach. And the maximum likelihood approach is the same as the ordinary least squares approach. It works on batch mode, which means that each time we receive new data and we want to use it and to enhance our results or to enhance the regression line, we need to run the maximum likelihood algorithm over all data set at once. In today's topic, we will use a third approach, which is the Bayesian approach, where we employ not only the maximum likelihood approach, but we use the likelihood probability plus a prior probability to estimate the regression line. And the advantage of this mode of this approach is that it works on online mode, which means that we do not need to build our model from scratch each time we receive new data. And this is a very important advantage, especially if you work with big data volumes. Then you may need such approach to be more easy to use and to be more easy to be updated without the consumption of very sophisticated hardware infrastructure. So the Bayesian approach enables us to obtain a fitted regression line and to estimate the level of noise that comes with our data, and also it works on online mode, which is the advantage of the Bayesian approach over either the ordinary least squares or on the maximum likelihood approaches we have learned before. Now let's see how Bayesian linear regression work and how we specify each part of our Bayesian model such that we obtain our predictions about the fitted line at the end of the algorithm. So we start with our data. In the simplest definition, we assume that we have a data set of two variables. A predictor variable x consists of n observations, and a corresponding target variable y consists of also n observations. And the linear function in this setting is very straightforward. We define y as a function of both x and w. X is the predictor variable, w is the set of coefficients, which is w0 and w1, and we can write the function in more compact form as w transpose x, which means the function is nothing but the product between the vector of coefficients and the predictor variable. In addition, we assume an extra parameter which expresses the noise parameter, and this is the same technique we have followed in our last video when we were talking about maximum likelihood approach. So we add an extra noise parameter epsilon. Epsilon is the residual between the true and the predicted value of our model, and we assume also that the noise parameter epsilon is normally distributed with zero mean and constant variance sigma square. So this is also again the same setting we have used in our maximum likelihood approach in the last video. The noise variance sigma square here, we usually replaced it by its inverter beta, and we call beta as noise precision. Instead of noise variance, we calculate the inverse of sigma square, and we call this parameter beta. So we can define the probability of our noise distribution as a normal distribution of zero mean and a variance of beta minus 1. Next, we define the likelihood function, how we can define the probability of our data. So having the above linear equation, we define the likelihood function by assuming that our predictor x is again normally distributed. So we're working in a fully Gaussian environment in this tutorial or in this video. So we consider the likelihood function of the target variable y given w and x and beta as a normal distribution of w given the f of x and w, the linear regression function we have already in the last section, and the variance of this distribution is the noise variance, exactly as we did in the maximum likelihood approach. So we have in more compact form, the likelihood is a normal distribution of w transpose x and beta minus 1 as our data variance or as the noise variance of our approach. The likelihood here is just again a normal distribution with the mean as the scalar product of our predictor x and the vector of coefficients w, and the variance is nothing but the noise variance or beta minus 1. Next, we define our prior, and this is the new probability that we add to the likelihood probability in order to obtain the full Bayesian setting of our approach. And remember that the prior is the distribution or the probability of our model or of our list of coefficients w. In order to select the prior for our settings or for our approach, we need to select something called a conjugate prior. The prior is called usually conjugate if it belongs to the same distributions family as the posterior. And as I mentioned before, that we are working with a Gaussian environment or a normal distributions environment, and therefore we will use prior of the family normal distribution. We select our prior to be Gaussian or normal with zero mean and spherical covariance. So the probability of w or the prior distribution is normally distribution around the zero mean, and we have here spherical covariance defined by alpha minus 1 times the identical matrix I. And note here that the prior distribution is a multivariate Gaussian distribution and not a single variate or a univariate Gaussian distribution. Why we use here a multivariate Gaussian distribution? Because as I mentioned before, that here we are trying to model the list of coefficients, the list of linear coefficients W. And in its short definition, W consists of two variables in minimum. We have in the shortest definition of a linear function, W consists of the Bayes and the slope of the regression line. Therefore, we have minimum two variables, and therefore we need to adopt multivariate Gaussian distribution to obtain these two values of both means and variances each time we update our algorithm. So again, in its short setting of W, in our case here, we need two values of the prior distribution. We need the average to have two values, and we need the corresponding covariance to have this definition. It's 2 by 2 matrix of alpha minus 1, 0, and 0, and alpha minus 1. And here alpha is an extra parameter in our specification, and it is called the prior precision. So we select here the prior mean to be centered on the origin in the offline mode before we receive any data, and this mu will be updated each time we receive new data until we converge to the correct regression line we aim to reach after some steps or after a certain level of data size we obtain. And as I mentioned before, the parameter alpha is a predefined constant in our specification, and it is called the prior precision. And this parameter should be defined before we start in our algorithm, or in other words, we need to define it in the offline mode before we start receiving data. Now, as we have the likelihood and the prior distributions, we are ready to write down our posterior. The posterior is again should be of the same family as the prior, so we expect the posterior to be a multivariate Gaussian distribution. It has the same probability density function (PDF) as of the prior, and we write the posterior probability as follows. We write that the probability of W nu, this is the new values of coefficients that we will calculate by multiplying the likelihood and the prior probabilities or distributions, given the initial W and the X and Y variables, our data. And this is a new multivariate normal distribution with the moments mu, nu, and sigma, capital sigma nu. And the posterior parameters are calculated as follows. The covariance of the posterior distribution is equal to the prior covariance to the power of -1 plus beta x transpose x, all to the power of -1. And this expression is equal to alpha times I plus beta x transpose x, all to the power of -1. After obtaining the posterior covariance matrix, we employ it to calculate the posterior vector of means or of averages, and the mu nu in this time will be the product of the posterior covariance times sigma -1, sigma to the power of -1 mu plus beta times x times y. As we may note in these equations, in order to compute the posterior distributions or the posterior distribution, we need to have initial definitions of prior precision alpha noise precision beta, so here alpha, here we also need definition of beta, plus the prior mean and the prior covariance, which are the bold mu and the bold or capital sigma in our specification. We need all of these values to be predefined in the offline mode before we start to generate posterior values. Okay, now as we have the complete Bayesian specification, we are ready to predict values of y using these specifications. After setting all of the above specifications, we start to generate what we call the posterior predictive distribution, which is the probability of y nu given x and y and alpha and beta. All of these are predefined, as I've mentioned before. And this new probability, or this new distribution, probability of the conditional probability of y nu, is equal to the integral of the probability of y nu given x and w and beta times the probability of w given y and alpha and beta. And the moments or the variables of this predictive distribution is defined as follows. The mu nu, which is the same as the y nu, this is the prediction that we are generating using our model, is equal to mu nu transpose times x, and the sigma square nu, which is the expected variance or the expected noise that comes with our model, with our prediction, is equal to 1 by beta, or beta minus 1, or which is equal again to the noise variance we have defined before, the sigma square, plus x transpose times sigma nu times x. And it is worth here to mention that regarding the definition of the generated noise level that comes or that surrounds the predictions y nu, we note here that we have two terms in this definition, or in the definition of the predicted noise level. The first term is or represents the data noise, which is the variance, the variance of the noise distribution we have defined before, and the second term represents the uncertainty about the model itself, or the list of coefficients w. And as these have been generated by using different distributions, therefore we add them up instead of multiplying them, because they have been generated from different Gaussian distributions. This is why you add them up. And it's also worth to mention that as much data we receive in this algorithm, as much low value we obtain from the second term. So if we have, if our data is very, very large, or it is theoretically goes to infinity, this second term will converge to 0, and this means that the noise level comes with the predictive distribution will converge to the noise level we have predefined, and this is accordingly means that the Bayesian approach of our that we are employing here will converge to the maximum likelihood approach, or to the frequentist approach. And this is a fact that I have also mentioned before in my previous videos about in this series, when I said that the Bayesian approach is different from the frequentist approach, as long as we have a reasonable data size or small data size. But if the data size went theoretically or goes theoretically to infinity, then the Bayesian approach will definitely converge to the frequentist approach, or in our case to the maximum likelihood approach we have discussed in the previous video of this series. Now we'll discuss the word procedure of the Bayesian linear regression. The first part regarding the inputs of our algorithm. We have usually 4 inputs. The first 2 inputs are mainly the data set. We need a minimum 1 predictor variable and 1 target variable, x and y. Second, we need to have an initial guesses about the linear coefficients W0 and W1 in order to build the regression equation. And we need to use initial guess of prior precision and noise precision in order to build both noise distribution and prior distribution of our Bayesian settings. Then we make a setup process. This is the offline process before we start to learn from our data. This is about model selection. So we select probabilistic distributions for both the data, which is the likelihood, and for the list of coefficients, which is the prior distribution. And the prior distribution again must be conjugate to the likelihood distribution in order to obtain correct posterior values or posterior probabilities. And this part is done before we start to receive our data. The last part of our procedure is the online part or the update part, where we start to receive new data observations. We use these data observations to calculate or to update the prior distribution and obtain new values of the list of coefficients, list of linear coefficients, which we call W nu. These are the posterior distribution or the updated version of the coefficients, and we accordingly calculate the predictive distribution, the probability of y nu, and we set the obtained posterior distribution as the last prior distribution, and we repeat this process again as long as we receive new data. And this process is continue to be executed each time we receive new portions of data. And this is the advantage of this Bayesian approach over both ordinary least square and maximum likelihood approaches, which are working only on batch mode. Now, as we have learned about the theory behind the Bayesian linear regression, I want to walk with you through an evaluation of both synthetic and real data sets. Let's start with synthetic data set. I have generated this simple data set of x and y. Sorry. Yes. I have here y equals to minus 0.3 plus 0.5 times x plus a noise distribution of 0 mean and 0.04 variance. This is synthetic data with normally distributed noise added to it between x and y. We treat x as our predictor, y as our target variable, and we start to learn our regression model using the Bayesian linear regression approach we have discussed. Here we have the plot of posterior distributions after receiving different number of data observations. As you can see here, at the first data observation, we have here the star represents the true value of our coefficients W0 and W1. This is the true value, and the generated posterior distribution seems to have very large value of variance surrounding the true observation, which means that the correspondent predictions shall have very large value of or very large level of uncertainty surrounding the predictions generated by the algorithm at the first point. As long as we receive more data, the variance of the posterior becomes less and less until it becomes very close and very concentrated around the true coefficients value, which means that the algorithm starts to converge to the true coefficients and start to discover the the correct coefficients of the true regression line after about 15 observations of data we have received, the algorithm received. The second list of plots here shows the true regression line. This is again the line that have been generated using the OLS, or the ordinary least squares approach. We take it as our baseline, and we see here if we generate some random samples of the posterior distribution, they are very dispersed regarding the true regression line, and this dispersity of the posterior samples become less and less as long as we receive new data. So here the random generated lines become more close to the true regression line, and after receiving about 15 data points, the regression line, the random samples of the posterior distribution becomes very close to the true one, to the true regression line. Here we in this set of plots we compare the true line in the black color with the predicted line in the blue line, and as we can see here that at the first point the both lines are a bit in completely different places, and also we noted that the uncertainty level or the noise level comes with our prediction is very high. This predicted line becomes closer and closer to the true line as long as we receive new data, and also in parallel the level of noise becomes smaller and smaller as long as we receive new data, until we converge to a stabilized results after about 15 observations, where we have already the both true and predicted lines are almost identical, and also the noise level become stabilized over multiple regions of our data set. Here we have another way to evaluate our model, which is to calculate the MSE metric of both true and predicted lines. MSE stands for the mean squares error, and as we can note here that if we compare the MSE metric with the increase of data size, we see that at the first couple of points the MSE of the predicted and true lines are reasonably or rationally higher than the other data sets, and as long as we receive more data observations, both true and predicted lines start to obtain lower range of mean squares errors, until both methods or both algorithms converge to the same values after about 200 observations. And this is again a proof that the Bayesian approach converge, which is the red line, converge to the maximum likelihood approach in green line after certain number of data observations. Here is the same fact, but in another shape. This is another evaluation metric called the prediction interval. Here we specify a certain confidence level of our predictions, and we see here for a data set of 100 observation, we can obtain a prediction interval of 95%, very smoothly, which means that we can say with 95% confident that our predictions will not exceed the upper prediction and lower prediction in the dashed lines, green and red lines. Of course, we have 5% outliers, but we can say after 100 observations that we are 95% confident that our predictions will not exceed the levels of uncertainty or the noise levels we have already obtained from our algorithm. And this is again another evaluation metric about that we can evaluate the preciseness and the performance of our Bayesian linear regression we have discussed in this video. Now let's move to a real data set to evaluate the same approach on it. Here I'm using a data set of both weights and heights of a population of a group of people. And I have used here this formula to define the linear function of our height and weight variables. So I've said that weight equals minus 0.13 plus 0.75 times height plus a noise distribution of 0 mean and 0.028 variance. Here I've normalized both variables between 0 and 1 to make the statistics and to make the calculations more feasible in the program. Again, I repeated the same sets of plots mentioned in the synthetic evaluation and the synthetic data evaluation. As you can see here, the variance of the posterior distribution is very high and is not really centralized around the true values of W1 and W0 around the model values. And as much data we receive, when we receive 8 observations or maybe 20 observations, the model becomes more and more compact and more and more, less and less noisy around the model we have already selected. And by the way, I'm here, the coefficients I have started with this real data set are not the true regression coefficients that have been generated by the OLS algorithm, because I wanted to see after how many observations the model will converge and will manage to detect and define the true coefficients of the linear regression line. So these are close to the true coefficients, but they are not exactly the values of the true coefficients. If we compare the second set of plots, the true regression line by some generated samples of the posterior over different data set, over different data sizes, we can see here that the generated samples are very dispersed from the true regression line at the first observation, at the first data observation. The posterior samples become more and more converged and more closer to the true regression model or to the true regression line as we receive more data, until they are very close to the true regression line after receiving 20 data observations. Again, here we can see here that the level of uncertainty is minimized as long as we receive more data observations, from 1 observation to 8 to 20 data observations, and the corresponding predicted line become closer and closer to the true regression line as we receive more data observations. Again, here if we compare the mean squared error values of both predicted and true lines, we can see again that of course the whole metric is very small because we have already normalized our data set before starting the algorithm. But again, it is very highly ratioed in the beginning of the data set, and it comes smoothly stabilized after maybe 200 or even 300 data observations. We come very close to the errors become very close to each other in both true and predicted regression lines, and also they are seems to be more stabilized and more close to each other, which again reflects the convergence of the Bayesian approach to the frequentist approach as much as the data size goes to infinity or goes to very large volumes. And as you can note here, that the true the error rate of the true regression line seems to be more than the error value of the predicted line, and this is can be understood if we consider that the assumption we have made about the data noise may not be correct. So we have assumed in the early beginning that the noise that comes with this data set is normally distributed, and this may not be the case. So our assumptions may be wrong, and this is why the true values records also a bit higher volumes of errors corresponded to the predicted model that we have generated by the Bayesian approach. Again, we can use the prediction interval of 95% confidence that we can say for sure that our data will not be, or our predictions will not exceed the lower and upper bounds that we have already defined by the noise variance surrounding the prediction line. This has been calculated for a data set of 650 observations, and this is also again an indicator that our noise level is a bit confident, or is very highly confident, and we are sure that the generated predictions comes with certain levels of uncertainty or certain levels of noise surrounding them, and the predictions will not exceed, the true values will not exceed these upper and lower bounds determined by the generated noise level. And I would like to finish this video by mentioning some shortcomings that comes with the Bayesian linear regression model. The first shortcoming is about the assumptions we made in the offline part of our algorithm. As I have mentioned before, that we need to makes a lot of assumptions about the data distribution, about the noise distribution, and about the parameter or the coefficients distributions. And if any of these distributions went wrong, then the generated result will definitely go wrong at the end of the execution. And this is one of the shortcomings of the of employing Bayesian settings to machine learning problems in general, and specifically as an example of Bayesian linear regression. The second shortcoming is about the we define always the noise level to be constant over all data volume, and this may not be true in rare scenarios, as you may imagine that in a lot of real life data sets, each region of data may has a different level of noise, or may has different type of or different distribution of noise. And if this is the case, then the noise generated by the Bayesian linear regression we have discussed in this video will not be 100% precise. And one solution of this problem is that we can divide our datasets into regions and start to understand the noise level of each region separately and calculate it separately. But this is generally a shortcoming that comes with the specification of the noise levels comes with Bayesian linear regression when we consider it as a constant value. A third shortcoming of Bayesian linear regression is the sophisticated Bayesian analysis in case of non-Gaussian data. As you can see here, that we adopt the simplest approach of Bayesian linear regression, where we consider all of our distributions as normal distributions. If we want to select other families of distributions, then the analysis and the infer of the distribution moments and the distribution means and variances will be more complicated and need more mathematical efforts to obtain the correct values of these moments. And this is again another shortcoming of this technique, especially if we knew that always and always, if our data is going to grow exponentially, or even if we work with big data volumes, then the result of the Bayesian approach will converge at the end of the data set to the frequent tests approach, so more or less to the maximum likelihood approach. So yeah, this is a third point that we can consider it as a disadvantage of Bayesian linear regression. I would like to thank you at the end of this video. I know that this video is a bit longer than usual, but thank you for watching. If you have any questions about this topic, feel free to leave them in the comments below, and otherwise have a nice day. Thanks.